So, welcome to this course on transport processes. This is a course under the National Program for Technology Enhanced Learning, and I will be your instructor. My name is V. Kumaran. I am at Department of Chemical Engineering, Indian Institute of Science, Bangalore 12. So, I will briefly give you an introduction to why we are studying transport processes and what we will study in this course, and also to how we will go about our study. So, a very important part of all engineering processes is the transformation of materials. Okay. In most engineering processes, it is desirable to transfer raw materials to finished products. And this is an objective in many branches of engineering related to materials engineering, chemical engineering, biochemical engineering, and so on. And this transformation we would like to do in a repeatable, efficient, okay, cost effective, okay, and environmentally friendly manner. Okay, that is the objective. And these transformations are usually classified into one of two types. One is physical, which does not involve change in chemical composition, heating, cooling, melting, adsorption, and so on, freezing. These are all physical processes. And the other is what are called chemical processes, which do involve chemical transformations from reactants to products. These involve a few common things. One is motion of constituents, okay, relative to each other. Okay. Motion of constituents relative to each other. So, for example, you could have materials that are diffusing relative to each other in order to effect transformations. Okay. You necessarily have the transfer of heat. In both physical and chemical processes. Physical processes, for example, heating, cooling involve transfer of heat. Chemical reactions could be exothermic or endothermic, and they involve transfer of energy in the form of heat. And there are also forces that are exerted on the fluid. Okay. Okay. For example, an impeller, for example, mixes two fluids together. So, there is a force exerted. The flow in a pipe, for example, you have to apply a pressure difference between the inlet and the outlet. That involves forces that are exerted on the fluid and so on. Okay. So, they typically involve transport of constituents, that is mass transport relative to each other, transport of heat, and forces exerted, which is basically a transfer of momentum. So, these are the processes that we will study here. Okay. We will study these processes first of all in the fluid phase. Okay. You know that all materials can be classified as solids, liquids, or gases. Liquids and gases together are what are called fluids. Okay. So, you will study primarily in the fluid phase, and that is because you can have relative motion of constituents by diffusion in the fluid phase. That is difficult to achieve in the solid phase. Okay. Fluids are of two types, liquids and gases, and here we will make no distinction between the two different kinds of fluids, because the transport equations that we write are roughly the same for both liquids and gases. Okay. So, let me give you some examples of where we will use these transport processes. Okay. So, for example, if I have a reactor, okay, with an impeller in it, okay, which is basically undergoing a reaction between two constituents which is catalyzed by a solid particle. Okay. And you put in some constituents A plus B together, and at the outlet, okay, you have to remove the product. Okay. Okay. This gives you, let us say, A plus B going to C, some constituent, and this is a solid catalyzed reaction. In this case, it is not sufficient to put in the relevant quantity of A and the relevant quantity of B. If you just do that, you will not necessarily get the desired output. Since it is taking place at the surface of a catalyst, if I look close to the catalyst surface, okay, there is A that has to go to the surface. So, material from the bulk fluid has to transport to the surface, it has to react at the surface, and the constituent B has to come out of the surface. Okay. If you do not transfer sufficient amount of A to the surface, you will not get the reaction at the desired rate. Similarly, if B is not diffusing out, then the surface will be saturated with A and you will not get the desired rate. So, what are these transport rates and how do they depend upon the conditions? That is something we will study. Reaction could be exothermic or endothermic, and you could have, for example, heating coils in here, okay, which either add heat or remove heat. The heat has to be added in sufficient quantity such that for an endothermic reaction, the sufficient amount of heat is sufficient to transform the material. It is not enough to add heat in the heating coils. That heat also has to be transferred through conduction, either to the surface in the case of an endothermic reaction or away from the surface due to an exothermic reaction. If the heat is not transported in the correct quantities, if it is endothermic, then the reaction rates will fall because the material will cool. If it is exothermic, if the heat is not removed from the surface, then you could get runaway reactions. And you have to stir the system so that there is sufficient mixing such that all of these transport of A to the surface, transport of B from the surface, and the transport of heat takes place. So, what we will be studying is this transport at the microscopic scale, okay, during this course. Okay. And this transport process course, it assumes that you know some, you have done a basic course in, for example, unit operations or something like that, and you also have some basic knowledge of these processes. We will develop the mathematical methodology as we go through this course, and in the end you should be able to predict what are the conditions you should impose in this so that you get a desired outcome. Okay. So, that the transport of mass, heat and momentum takes place at the correct rates in order to get the desired outcome. So, during this course I will be following a textbook. Okay. So, this is the textbook. A link to this will be given on the course web page, so you can purchase it if you want. And this textbook has in it, okay, chapter wise discussion, okay, of all the all the material that we will be covering during this course, and the chapter that is being discussed will be provided in the course, in the lecture title itself. So, you can follow this book in order to get the lecture titles and refer to the book if you have any doubts, if there is something in the lectures that you do not understand. The book also has, at the end of each chapter, the book also has problems. Okay. There are more than 150 solved assignments. For example, you can see that this is one of the solved assignments, example 1.6.2. There are more than 150 solved assignments in this book, okay. And there are also problems at the end of the book, end of each chapter. Okay. So, some of these problems we will solve during the interactive sessions, okay, during the course. So, the course will consist of lectures and some assignments that we will give you. These exercises, as you can see, some of these we will solve as example exercises during the course through our online sessions. Okay. So, that is going to be a summary of the course, 30 hours, and we will go through transport processes starting from a unit operations approach, where we consider the entire system as just one unit, and we derive equations relating the rate of transport, average rate of transport, to the independent parameters through dimensional analysis. We will discuss dimensionless groups and correlations, and then we will go on to analyzing transport at the microscopic level. Okay. So, at the microscopic level, we will derive shell balance equations, and then we will solve these equations under specific conditions to show how the transport of mass, momentum, and energy can be predicted based upon correlations and based upon analysis, and how we can design processes in such a way that we get the desired outcome based upon the conditions that we create for the processes to take place, the processes of heat, mass, and momentum transport to take place in such a way that we can design processes for the desired outcome. So, that is a summary of the course, and if you are interested, please join the course and we will start our discussion. Thank you.